Hello everyone, this is John. Today let's talk about our last topic about the state machine design. So in this lecture, I'll give you some real-life examples to show you how we can use what we have learned to design some simple state machines that has real useful applications, and you can see them in our daily life actually. First, let's look at the general procedures to design a state machine. Actually, if you read this, you will find it's not that different from the steps to design a combinational logic circuit. But there's still some difference here. So like after we understand the question, figure out the input, output, we also need to kind of figure out what type of state machine we're going to use, how many states we need, how many flip-flops, right? And then we need to draw the state diagram. Once we have the state, a correct state diagram, we can generate the state transition table, including the flip-flops inputs. And the one thing you need to be careful here is that we are actually designing the flip-flop inputs, right? And we will use the flip-flop outputs as our input in this state transition table. If you remember, the present state will be the input. Okay. Then once we have the state transition table, we can find the Boolean expression for the flip-flop inputs. And if there are any asynchronous outputs, then we can also find Boolean expression for them here. Okay, finally just draw the logic diagram, including the flip-flops and the combination logic. Okay, let's look at our first example. Let's try to design a synchronous sequential circuit with one input X and one output Z. So Z is the asynchronous output here that recognize the input sequence 0, 1. So basically it says we have a data input called X, and when we input the data serially, okay, we should have an output to tell us that we found a fixed pattern in that data. So this is very useful, right? You can use this as a data pattern recognizer. Okay. So how to design a circuit to realize such a function? Because we notice that we have to recognize certain pattern, which means we have to save the previous result so we can tell if we got the whole pattern, right? So first let's look at some example here. Say if I have a series of data look like this, then what's the value for output Z then? Say the first bit of data is 1. If the first bit is 1, then there's no way, no matter what happened to the next bit of data, we won't get to 0, 1, right? So in this case, the system should not respond, which means we can set Z to 0. But also you can design a system using like active no output. But the design principle is similar. So here we just keep things straightforward. We use active high output. So if there's no such sequence, we just output 0. Then the next bit of data is still 1, which means it's still 0, right? Now the third bit of data is 0. This matches the first bit of pattern we want to detect. So there's a possibility, right? We can detect that pattern, but right now it's too early to tell the result. So Z is still the 0. We need to save this data and look at the next bit of data, which is also 0 here. So which means these two consecutive data is not 0, 1. So no output, no active output. But since this bit is also 0, which matches the first bit of pattern we want to detect, so we need to keep the system alert and check the next bit. And it's 1 here. So we got a 0, 1 here, which means at this moment we should output 1. Okay. Then we check the next bit, which is 0. So z is 0. And the next bit, the x is 1. So we got another 0, 1. So we should have 1 here. And then we have 0 here. This is 0, 0. So we have 0. Okay. So basically, we use some example to help us understand this question. Okay. Now we need to think how to build up the state machine. We need, and the first thing is try to figure out the state diagram. But to do that, first we'll need to know how many states we got here. So let's say we have an initial state S0. Okay. Then the S0 stands for, like, we have the first bit of data coming. It could be 1, could be 0. Then we need to figure out what result we should get for each case. So if x is 0, what will happen? Z is 0. And, let's start with x equal to 1. So if x is 1, z should be 0, as shown here, right? So, which means we didn't detect the first bit of the pattern. Okay, which means we don't make any progress. So which means we need to stay in this state. Make sense to you? So which means 1, 0. So x equal to 1, and we are at state 0, S0, the first state. So nothing gonna change. Then we will wait till the next bit of data. Since it's still 1, so still follow this arrow. Now we wait until next bit, which is 0. So when it's 0, which means we have detected the first bit of the pattern. Then we need to remember this state. So we need to go to a different state, which is S1. So S1 basically means we have detected the first bit. Okay. And to transit from S0 to S1, we need x to be 0 and the z to be 0. Okay. Then at S1, we need to detect the next input. Okay, since it's 0 here, which means we didn't get this pattern. However, this 0 can be used, can be thought as the detection of the first bit here, right? So it will stay here if it's 0. Then next, if we detect a 1, which means we found the pattern. Okay, and immediately we need to go back to the initial state to get ready for the next detection. Then we got, but at this moment, z will give output here, will give a signal here. So let us know, okay, we detect this pattern once. Then we start the next detection. So actually you will find we just need this 2 state to make this state machine. Since we have 2 states, so we can number state 0, number state 1. So we actually only need 1 flip-flop here. Okay. And now let's try to make the state transition table. So in this case, we have the present state Q, and we have input X. We have next state Q plus or Qn plus 1, either way, and we have output Z. Okay, so if we are at state 0 and X equal to 0, what we found? It will move to state 1 and Z equal to 0. If we are at state 0 but X equal to 1, we can tell it stay at the initial state and the Z is 0. However, if current state is S1 or 1 here, state 1 here, and X equal to 0, we will find the next state is still S1 or 1, Z is 0. But if X is also equal to 1, which means we detect the pattern and we need to go back to get ready for the next detection. So this will be 0, but the Z needs to be 1. Here, the current input Q and the input X is the input for this table. So now we have figured out the current state and the next state and the output value. Then we have to decide which type of flip-flop we want to use so we can design a circuit. So here, let's say I want to use the JK flip-flop, not D flip-flop. Let's try something different. If you remember JK flip-flop, J carries the rate set here. So whenever there is clock rising edge comes, if it's 0, 0, if you remember, the next state Q will equal to its current state. No change. If J equal to 1, if J equal to 0, K equal to 1, let's refer to the reset state. So output will be 0. If it's 1, J equal to 1, that is set state. Finally, if 1, 1, that's what we call toggle. If you remember, toggle means we always take Qn prime, the opposite. Okay. So how do we figure out the JK value here? Basically, we use this state excitation table for JK flip-flop and the state transition table here. Okay. So if current state is 0, next state is 1. So what does that give to you? So you can think where the JK flip-flop is changing from unchange to set. But it can also think as changes from reset to set, right? So we need to look at the reset and we need to look at the set. Okay, for set, JK is 1, 0. For reset, it's 0, 1. But it can also be like like toggle, right? So actually this is not, there are no reset because it's from 0 to 1. It can only be either toggle or set. So no reset here, sorry. Okay, so which means J has to be 1, but K could be 0, could be 1, which means we don't care about K. Whatever value it is, this change will happen. Okay. Now the next is changing from 0 to 0. So no change corresponding to either, we can think this is no change state, but we can also think this as reset state, right? So in this case, J has to be 0, but K again, we don't care. Then the next one, 1, 1, which means either no change or either set. No change or set. So in this case, we know K has to be 0, but J doesn't matter. Finally, 1 to 0, this could be toggle And also this could be reset, right? When we reset, it will change from 1 to 0 2, right? So this tells us k has to be 1, but j could be anything. Okay, once we have this, we need to use the color maps. So this is a two variable color map to get the expression for j and k. So for j, we have 1 0 xx. So 1 0 xx. For k, we have xx 0 1. Okay, so simplify this. We will get j equal to x prime and k equal to x and z equal to q and x, right? So once we have this, then we can draw the circuit. So we have a jk flip-flop here. This is the clock input. This j input, k input, q output. Then we have x input. So j actually equal to x. X prime, sorry. And k equal to x. And z equal to q and x. So that's the logic diagram to realize this sequence detector. So pretty simple, right? But we need to follow the sequences to do the design, so you won't miss anything. Now let's change the example one a little bit to make it a little bit more complicated. Okay, see if we can still do this. So again, let's design another synchronous sequential circuit with one input x and one output z, but this time we need to recognize a different sequence, which is 1 0 1, and it allows overlapping. Overlapping means we can use the result of the first detection as part of the result for the next detection. Okay, so I show you what does that mean. Still, we put some examples here. So say we have the data series look like this. Then how would the output react to this? Let's assume z is still active high. So it will give a logic 1 when it detects 1 0 1. Okay, so start with the first bit 0. The first bit 0, then there's no chance it detects 1 0 1, right? So this is 0. Again 0 again, so no chance. Then 1, it matches the first bit, so there is a possibility. So we need to be careful. Then the next bit is 0, matches again, be careful. Then check the next bit, which is 1. So we can have a 1 0 1 here, which means the z output will give us a signal 1 on it. And at the same time, this one can be used as for the first bit of the next detection. So we already have 1 here. Then we check the next bit, it's 1, not 0. So z should be 0 because there is no 1 0 1. And again, we will use this one as the first bit. Then check again, so it's still 1. So then we put a 0 again, and still use this as the first bit. Okay, then keep detecting. So the next bit is 0. Now it's matching the second bit. So but it's still 0 for the output. Then we have 1 here, match the third bit. So now we have another 1 0 1 here. So this should be 1. Okay. At the same time, we will use this one as the first bit. to continue our detection. Now we have another 0 here, which matches the second bit, and another 1 matches the third bit. So we have another output 1 here. Got the idea? So this is called overlapping. We can use the last bit of the previous detection as the first bit of the next detection. So that's called overlapping. Okay, now how do we design a state machine like this? So probably you notice that we should have at least one more state here, right? Because we have to detect one more bit of data. So which means we have to save one more bit of result here, right? So still, let's assume we have S0 as the starting state or state 0, okay? If we detect 0, what will happen? Which means we have no chance to detect the pattern. So it will keep at the initial state, like nothing happens. So when x equal to 0, z equal to 0, and it stay here. When it detects 1, which means it detects the first bit of the pattern, then we need to save. Right? So we need a different state, which is S1 or state 1. This happens when x equal to 1, z equal to 0. Okay, then next we need make detection again. If we detect a 1, another, let's follow this sequence. So let's say the next bit is a 0, which means we detect the second bit of the pattern, which means we need to save that data again, right? So we will need another state to save this, so which is 0, 0. Okay, but then let's go back to this state. What happens if we detect a 1? Like in this case, we first detect a 1 here, okay, but then here we detect another 1. There will be no progress, no 1, 0, 1, right? But we can use this 1 as the first bit, so which means we still detect 1 bit of the data, so it will stay here. Okay. Now, when we now let's continue. So say we have detected a 0 at the second bit of the pattern, and we move to this S2 state. At this state, if we detect another 0, which means it's not a 1, 0, 1, it's a 1, 0, 0, what will happen? There's no chance we can get a 1, 0, 1, right? Because we have 1, 0, 0, so which means it go back to the initial state. So which means 0, 0. However, if we detect a 1, then which means we have detected the 1, 0, 1 pattern, but at the same time, this 1 will be treated as the first bit of the next detection. So actually, you will find this will go back here if it's 1 over 0. Sorry, 1. We need output 1 because we have finished the detection, the current detection, and starting the next one. Okay. So how do you check if you consider all the possibilities? Basically, just check for each state if you have considered all the possible input values. Because we have one input here, so only 2 values. So for this state, we know where it goes when x equal to 0 and x equal to 1. For this state, I know where it goes when x equal to 1 and x equal to 0. For this, I also know like where it goes when x equal to 0 and equal to 1. So basically, we covered every possibilities. Okay, so that's the state diagram for this one. Now let's try to figure out our design. So the state transition table. So we still have current state, but since we have 1, 2, 3 states here, so we need 2 bits now, right? 1 bit is not enough. We have X. Then we have 8 combinations. Q1 plus, Q0 plus, and the Z. Okay. So if current state is 0, 0, which corresponding to S0, and X equal to 0, it go back to itself. Output is 0. If it's 0, 0, but X equal to 1, we know it go to state 1, which is 0, 1. This is still 0. 0, 1, 0. So if we're here and X equal to 0, we're actually going to S2. So it's 1, 0, standing for decimal 2, right? And 0, 1, 1 point to itself, so 0, 1, 0. And 1, 0, 0, so we are here. So we are at state 2 here. And if it's 0, X is 0, it go back to 0, 0. Okay. If X is 1, it go to S1, which is 0, 1. And the output is 1. So 1, 1, we don't actually have this state. Remember what to treat this? Just treat it as don't care, because we don't even use this state. It doesn't matter what value we have for this state. Okay, so the next step is to figure out what type of flip-flop we want. So here, let's say we use D flip-flop to make it simple. So for D flip-flop, the D input is basically equal to Q1 plus and Q0 plus. So to save some time, just put D1 here, D0 here. Okay, so we need 3 column maps. This time is 3 input column maps. Okay, so we have, so for D1, we have 0, 0, 1, 0, 0, 0, X, X. Okay. For D0, Q0. We have 0, 0, no, sorry, 0, 1, 0, 1, 0, 1, X, X. Finally, for Z, we have 0, 0, 0, 0, 0, 1, X, X. Okay. Then we do the simplification and write down the Boolean expression, which is, so this is Q0 X prime. So D0, actually we can do this grouping. We have X, and for Z equal to Q1 X. Okay, then you just need to draw the logic diagram. You can realize this circuit.